Imagine every single particle in your body, in the Earth, in every star, is governed by pure chance. Quantum mechanics says nothing is ever certain. An electron can literally be in two places at once, and events happen by rolling cosmic dice. So, if the foundation of reality is probability, why hasn't the universe randomly deleted itself in the last 13.8 billion years? Why don't atoms just spontaneously explode, or all the protons in the universe decay at the same moment, turning everything into radiation? The truth is far more mind-blowing. Quantum probability is the most tightly controlled, rigid, unbreakable system nature has ever invented. When quantum mechanics was born in the 1920s, it felt like physics had opened Pandora's box, replacing Newton's clockwork universe with probability waves. Einstein famously rebelled, stating, "God does not play dice, and Schrödinger created his cat thought experiment to mock how absurd it all seemed." Because if the microscopic world is truly probabilistic, how does the macroscopic world stay so insanely stable? Let's kill the biggest myth right now. When people say quantum mechanics is probabilistic, they imagine pure anarchy, but that's dead wrong. The core law that runs the entire universe, the Schrödinger equation, is 100% deterministic. Give it the wave function at time zero and the energy rules, and it will tell you exactly what the wave function will be in a trillion years, with no randomness or exceptions. This evolution preserves every drop of probability perfectly. Nothing ever leaks. Nothing is ever created or destroyed by chance. On top of the Schrödinger equation, the universe has unbreakable conservation laws: energy, momentum, angular momentum, electric charge, and baryon number. These aren't statistical tendencies. They are absolute prohibitions written into the fabric of quantum field theory. Thanks to Emmy Noether's theorem, every symmetry of nature gives us a conserved quantity, meaning spontaneous processes that would destroy the universe are either completely forbidden or astronomically suppressed. For example, proton decay, predicted by many theories, has an experimental limit greater than 2 times 10 to the 34 years, vastly exceeding the universe's age. Go back to 1911, Rutherford discovers the atom has a tiny nucleus with electrons orbiting, but classical electromagnetism predicted disaster. An electron should spiral into the nucleus in about 10 to the minus 12 seconds, causing the entire universe to collapse almost instantly. Quantum mechanics saves the day with one magic trick, quantization, where energy levels are discrete, with no in-between. The lowest rung, the ground state, is as low as it gets. There's literally nowhere lower to fall. Now we get to maybe the single most underappreciated rule in all of physics, the Pauli exclusion principle. No two identical fermions, like electrons, can occupy the same quantum state, forcing electrons to stack into higher and higher energy levels. Without Pauli exclusion, every electron in the universe would drop to the lowest possible state, causing matter to collapse to insane densities. It's also why solid objects feel solid. When two atoms get too close, their electron clouds can overlap, resulting in an incredibly strong repulsive force. Okay, so atoms are stable, molecules are stable, but what about Schrödinger's cat and all that weird superposition stuff? Here's the answer almost nobody talks about: quantum decoherence. Macroscopic objects are never isolated. A dust speck is constantly getting pinged by air molecules, photons, cosmic rays, roughly 10 to the 23 interactions per second. Every single interaction entangles the object with the environment, and within an absurdly short time, any quantum superposition becomes completely scrambled across the universe. The classical world emerges not because quantum mechanics stops working, but because the universe is too nosy to let superpositions survive. Quantum mechanics, often associated with uncertainty, is paradoxically the very foundation of our universe's remarkable stability. Let's explore how this seemingly chaotic realm actually ensures the cosmos remains a robust and predictable place. Consider a room filled with air, containing an astronomical 10 to the power of 23 molecules, each performing quantum gymnastics. While individual collisions are probabilistic, the sheer number of these random events, when averaged, leads to incredibly small fluctuations. This is the powerful law of large numbers in action, a principle that underpins much of our observable reality. Concepts like temperature, pressure, and entropy, the smooth and predictable laws of thermodynamics, emerge directly from quantum probability averaged over these immense numbers of particles. Even the arrow of time and the second law of thermodynamics, which states that entropy always increases, are consequences of this statistical averaging. Microscopically, the laws of physics are time-reversible, meaning they work the same forwards and backwards. However, macroscopically, entropy always increases because there are vastly more disordered states than ordered ones, making disorder statistically inevitable. Now, let's address some of the truly scary scenarios people often raise, and why they aren't actually nightmares. One such scenario is false vacuum decay, the idea that our universe's vacuum might not be in its true lowest energy state. What if a bubble of true vacuum nucleated somewhere, expanding at the speed of light, rewriting the laws of physics and destroying everything? Current calculations, based on measured Higgs and top quark masses, suggest our vacuum might indeed be metastable. However, the expected lifetime of this metastable state is an astonishing 10 to the power of 100 years, or even far longer. That's a googol years. To put it in perspective, the universe is only 13.8 billion years old. We are safe by a margin that literally breaks calculators, making this theoretical threat practically irrelevant. Another critical aspect is the fine-tuning of the universe's fundamental constants. Even a slight change in the strong nuclear force, by just 1 to 2%, would mean no stable carbon and thus no life. Similarly, a minor alteration to electromagnetism would cause atoms to either fly apart or collapse entirely. These constants are dialed in with insane precision, ensuring the long-term stability required for chemistry, stars, and life itself. Whether you attribute this to a multiverse, the anthropic principle, or divine design, the undeniable fact is that the physics works. So, why do people often claim that quantum mechanics implies anything can happen? Technically, anything not explicitly forbidden by the laws of physics can happen, but the probability can be infinitesimally small, like 10 to the minus a trillion. This isn't anything can happen. It's effectively never in the entire history of the universe. Let me pull this all together. Quantum mechanics doesn't threaten stability, it guarantees it. Here are the layers of protection the universe has built into itself, thanks to quantum mechanics. First, the deterministic, unbreakable evolution of the wave function ensures predictable behavior at its core. Absolute conservation laws forbid catastrophic processes, maintaining fundamental balances. Discrete energy levels prevent atomic collapse, ensuring matter's integrity. The Pauli exclusion principle gives matter its volume and solidity, preventing all electrons from occupying the same state. Decoherence rapidly kills macroscopic superpositions, ensuring our classical world is stable and unambiguous. Statistical averaging over 10 to the power of 23 particles produces the smooth, predictable classical behavior we observe daily. Finally, exponentially suppressed tunneling rates prevent any dangerous quantum processes from occurring frequently. And the fine-tuned constants keep chemistry and stars working for billions of years, allowing for complex structures in life. Quantum mechanics didn't almost destroy the universe. It built the most bulletproof cosmos imaginable. The universe isn't a fragile snowflake that somehow survived 13.8 billion years of quantum coin flips. It's a fortress with every apparent source of randomness locked inside layer after layer of mathematical rigidity. Quantum probability isn't chaos wearing a lab coat, it's order in disguise. And that, paradoxically, is the deepest reason we're here to wonder about it at all. If this video made you see quantum mechanics in a completely new light, please hit that like button and share it with a friend. Drop a comment. Which layer of protection blew your mind the most? Pauli exclusion? The 10 to the power of 100-year vacuum lifetime? Or decoherence speed? And if you want more videos that delve deep without oversimplifying, subscribe and ring the bell. I'm already working on the next one. Thank you for spending time with me, geeking out over why reality is still here. Stay curious, keep questioning, and I'll see you in the next one.